rushed at the end of the semester because I kind of rushed this year for things. I wanted to do some sample problems for you to help you out with the Chapter 13 problems that are going to be due on Friday, January 6th. And so these are my notes. I uploaded them onto Google Classroom, and there's some examples on here, but I just want to talk our way through a little bit of that. So I think I had gotten through most of these, page 4 to page 5, I think. We did talk about this, I think, a little bit as being the continuity equation. So it's basically V times A would have to be constant in a closed system, in a closed pipe, kind of like the current in a series circuit has to be the same everywhere. So that's why narrow parts have a faster flow rate. And that's described by this. Velocity 1 times cross-sectional area 1. Usually you get cross-sectional area by doing pi r squared if it's a circular pipe. This nasty beast is Bernoulli's equation, but I did say that normally it's not quite as bad as we would think about, or as it initially looks, basically because of the fact that many of these things you can either cancel out or are known when you're given the problem information. And section 13.5 talks about that. We talked about that a little bit as well. One key thing is keep things in standard units when using this equation, and that means we have to use absolute pressure for these, not gauge pressures. Oh yeah, sample 13.5, that was the Prairie Dog one, which is kind of cool. Chapter 13, sample problems. So I'm going to go through a few of these. These are in the back of your book, and I think I'll probably go through this one, problem 26. I'll do example 3. Yeah, probably 9, 34, example 3. And then it's problem 26. Okay. So I'm going to take a look at this. I'm going to get my textbook out. Prairie Dog is such a fun example. It's on page 459. Okay. So for problem number 9, it says a tall cylinder contains 25 centimeters of water. Oil is carefully poured into the cylinder where it floats on top of the water until the total depth is 40 centimeters. What's the gauge pressure at the bottom of the cylinder? So the gauge pressure means we don't need to worry about atmospheric pressure. I think the book uses 101,300 pascals as atmospheric pressure. I think the AP is fine with it being 100,000 if you need to use it. So just like how you can use G as 9.8 or 10 meters per second, a lot of times I would use just the simpler version, 100,000. So the other part then is asking about the absolute pressure, which I asked. The book did not. Okay, so the gauge pardon me, I'm getting over a cold here over break. Hopefully it'll be okay by the time we come back. Gauge pressure is equal to this formula, which is density times G times depth of the oil plus density times G times depth of the water. So essentially, density is mass per volume. So when we multiply this by newtons per kilogram, we're looking at weight per volume. And it's essentially figuring out the weight of all that liquid. So in this case, we've got 900 kilograms per cubic meter, 9.8 newtons per kilogram, 0.15 meters of oil. And this is in a table earlier in the textbook, so you will need to refer back to that table in chapter 13. This one, 1,000 kilograms per cubic meter, 9.8 newtons per kilogram, 0.25 meters of water is still in there. So we get, I think this was 1,320 plus 2,450, 3,770 pascals. If you want to find out the absolute pressure, We have to add in the pressure of the atmosphere. Here I happen to use the official version from the textbook, which is 101,300, so I get 105,100 pascals. For problem 34, we have a pump. It's used to empty a 6,000 liter wading pool. The water exits a 2.5 centimeter diameter hose at a speed of 2.1 meters per second. How long will it take to empty the pool? Well, first of all, we've got a volume, but I need to put things in correct units. So in units that agree with each other. There's a few ways you could do that. A liter is 1,000 milliliters, and you could also think of that as 1/1000th of a cubic meter is a liter. If you're not sure about how to do that, I understand, but you would want to get this in cubic meters, I think. So next thing is if we've got this volume of water, now we need to find the volume flow rate. So that's the area times the speed. So we were told that it was a 2.5 centimeter diameter hose. So the area is pi r squared. That's 1.25 centimeter radius, or 0.0125 meters. So this is the area. So the area times the speed gives us the volume flow rate. So that's 1.03 times 10 to the negative third cubic meters per second. So now if I think about this, this is a general equation. If I've got a certain quantity divided by a rate, that'll give me time. So you really want to look at your units to see how you set this up here. I end up getting meters cubed divided by meters cubed per second, which gives me units of seconds. So I get about 5,800 seconds. That's about 1.6 hours. Example 3. So petroleum companies often use pipelines to transport products for long distances. The Keystone Pipeline is a good example of that. Alaskan Pipeline's another. So assume a gasoline pipeline, so gas is 680 kilograms per cubic meter, transports gasoline over a hill. The diameters of the pipeline are shown, as is the gauge pressure and speed at the top of the hill. So we've got something like this. 0.4 meter diameter, 1 meter diameter here, 30 meters is the hill, moving at 2 meters per second, 40 kilopascals of gauge pressure. So first, to determine the speed at the bottom of the hill, we're going to use the continuity equation. Area 1 times velocity 1 equals area 2 times velocity 2. So the area 1 would be pi r squared times v1 equals pi r squared times v2. So if I want to know the volume flow rate, I would actually have to multiply this by pi. I don't. I only want to find the speed. So this is 0.2 meter diameter, or 0.4 meter diameter, so it's 0.2 meter radius. So pi r squared, 0.2 meters squared times 2 meters per second. So I end up getting this as 0.32 meters per second. So it's flowing much slower down here, which makes sense because it's a wider pipe. Determine the absolute pressure at the start of the pipe. So this is the Bernoulli equation, dun, 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 and notice I have to use absolute pressures here to get the correct calculation. If I want to find gauge pressure here, I would also end up make sure everything is in absolute pressure initially and then convert back, just because I don't want to screw around with possibly making an algebra mistake. So this is what I'm trying to find. We know the rate at which we're flowing here. We just found that out. The density of gasoline is the same for all these terms. So 1/2 density, velocity 1 squared. That's basically the kinetic energy, right? Rho gy1, well, this is at the bottom, so I'm going to call that 0 to make my life easy here. This pressure at the second spot, 40,000 kilopascals, or 40,000 pascals was the gauge pressure, but the atmosphere is 101,300. So I'm going to put 141,300 here. 1360, 1/2 density times v squared. And then because we've raised it up so much, it has an additional large amount of large number here caused by having to push that up. So that means we need a pretty darn high pressure here. 680 is the density, 9.8, 30 meters, it's lifting it up. So this 34.8, which is due to the speed this thing is moving, is basically inconsequential. But it comes out to gauge pressure at the bottom would be 241,200. The absolute pressure at the bottom would be around 342,500-ish, 540-ish. So I said determine the absolute pressure. That would be this amount here, the 342. The gauge pressure is 241. So I was kind of inconsistent with how I asked about that. These are a couple you could look at. This is another one I want to go over because it's a density one, which I think is useful. Problem 26 out of chapter 13. So we've got water, so the density of that we know is 1,000 kilograms per cubic meter. We've got a 75 cubic centimeter sphere of plastic, the density of 840 kilograms per cubic meter. And we're asked to determine the tension on the string. So this is less dense than the water, so if the string were cut, it would float. So I'm going to draw a free body diagram to help me think about that. So I've got buoyant force, it's just acting up. Tension of the string, which I'm trying to find out, is acting down. And then the gravitational force on the plastic is also acting down. So if this string is holding it, we know that force up equals force down. So buoyant force equals gravity plus tension. The buoyant force is the density of the water times the volume times g. So if I've got 75 centimeters, cubic centimeters of plastic, then that converts to 7.5 times 10 to the negative fifth cubic meters. If you're unsure about how to do that on your calculator, the simple conversion factor is there's 1 meter for 100 centimeters, but you're doing that in 3 dimensions. So I would multiply this by 1 over 100 and then cube that quantity 1 over 100. So you're basically dividing by 1,000,000. So that's the volume. And so I get 0.735 newtons is the buoyant force. The gravitational force on this plastic, or the weight of it, is going to be equal to mg. Well, the mass is equal to density times volume. Well, we found out the volume right here. The density of the plastic is given. So the density is 840 multiplied by 7.5 times 10 to the negative fifth times 9.8 newtons per kilogram. So the gravitational force, or the weight of the plastic, is 0.6174 newtons. So therefore the tension is going to be about, yep, they do that even on break, 0.118 newtons. There's another example for you if you want to look at those, but like I said, I want to go through a few.